Hello and welcome to the Unit 7 Section 1 video on exponent rules. So in this unit, we're going to be talking about exponents and how you work with them, and we're going to start off by talking about monomials and like terms. So a monomial is a number, a variable, or a product that has numbers and variables with whole number exponents. So for example, here's a look at what some monomials are. So it can be a number. It can be a variable, such as y. It can be a number times a variable. It can be a number times a variable with the variable taken to some power. And in this case, it's got to be a positive power, okay? Or it could be a fraction times some sort of collection of variables, okay? Those are all monomials. In contrast, these are not monomials. You have the square root of x. Anything that's under a square root or a cube root or a fourth root symbol or so on is not considered a monomial. Neither is something that has a variable in the denominator. So you cannot have some variable like y here in the denominator. You also can't have more than one term. 3 minus 4ab is actually two monomials put together. Okay, so the operation adding and subtracting will string monomials together. So monomials are going to be separated by addition signs or subtraction signs, and those monomials will be your terms, but you can't have more than one term and it be a monomial. Okay, so here 3 is a term, negative 4ab is a term. Again, you can't have a variable in the denominator. Having a power on that variable does not make a difference. And you cannot have a variable to a negative exponent. The exponent has to be positive. So let's move on down and see if we can identify in example 1 whether or not we have a monomial. So for A, we certainly do have a monomial because we have a number times a variable. That variable's to a power, but everything's in the numerator, so we're good. For B, we have a variable in the denominator, so that would not be a monomial. For C, again, we have a combination of numbers, variables. Some variables are two exponents, but that's fine, so we have a monomial. Same goes for D. E, we have a square root symbol, so that is not a monomial. And then finally for F, we have a fraction, but it's okay to have a fraction as long as it's just part of the number. The variable is in the numerator, is not in the denominator, so F is a monomial. Now, many monomials consist of a base, exponent, and coefficient. So the coefficient is your number out in front. Your base is your variable, or it could be a number taken to some power, okay? So here, the power is 2. That's your exponent. So the base is the number or variable being raised to an exponent. The exponent is the number that indicates how many times the base in a power is used as a factor. And the coefficient is a number that is multiplied by a variable. So you can only have a coefficient be a number. It cannot be a variable. So in example 2, let's identify the base, exponent, and coefficient of the following terms. So for A, our base is y because y is being taken to some power. So our base is y. Our exponent is 3, which is the power. And then our coefficient is the number out in front, negative 7. For B, our base is x. Our exponent is 5. And our coefficient is the number in front, 14. For C, our base is x again. Our exponent is the power that we're taking x to, which is 12. And you're going to want to say there's no coefficient, but there is a coefficient. It's just not written down. Our coefficient is 1. And we don't have to write the 1 in front of the x because 1 times x to the 12th is just x to the 12th, so we don't write it down. But there is an understood 1 out in front of that x to the 12th. And then finally, for D, our base is a. Our exponent is negative 7. And our coefficient is negative 1. Like terms are terms that contain the same variables with corresponding variables raised to the same power. So they have the same base with the same exponent. The coefficients can be different. So in example 3, let's list the like terms in each set. So we have 5x squared, but there's no other x squared terms. So we're going to leave that out. Then we have 6xy. Well, we also have a 7xy. So there are two of your like terms. And then 4x and 5y, they don't have anything that go with them. For b, we have negative 2xy squared. Well, if you look down the list, we also have a 7xy squared. So those are like terms. 3xy doesn't have anything that goes with it. Negative 4x squared y doesn't have anything that goes with it, and neither does 2x. For c, we have 7ab. If we look down our list, we have a negative ab, so there's two like terms. Then we have negative 3a. If we look down the list, we also have a negative 14a, so those are like terms. And those are all the like terms that we have in that one. In D, we have 7x. We also have a negative x, so those go together. And then we have 9xy and 8xy, and those two go together. A power can be expanded by multiplying the base by itself the number of times indicated by the exponent. Conversely, a number or variable multiplied by itself can be collected into an exponent. So here, if we do 5 times 5 times 5 times 5, that's 4 of them. So we can collect that as 5 to the 4th. We also have an x times x times x. We can collect that into x to the 3rd. And then y times y is, of course, y squared. So let's do a few examples of these. So we're going to write, in example 4, we're going to write the following using exponents. So we've got 4 times 4 times 4 times 4 times 4. That's 5 of them. So we can take 4 and raise it to the 5th power. For b, we have 4 x's multiplied together, so that's x to the 4th. We can also separate things out. In example 5, for part A, we have 5 to the 3rd, so that's 3 5s. X squared is 2 x's, and then y to the 4th is 4 y's. For b, we have negative 4 squared, so that's 2 negative 4's multiplied together. X to the 4th, so we're going to multiply together 4 x's, and then we have the y on the end. Now that we have a good sense of how exponents work, let's talk about some of the rules of exponents so that we can actually do some algebra with them. So here we have the product rule. Recall that an expression of the form x to the n is a power. The base is x and the exponent is n. So here I've listed our powers of 2 from 2 to the 1st, 2 to the 10th, just as reference, because we're going to do a little bit of exploration. We know that 4 times 16 is 64. Let's rewrite 4, 16, and 64 into powers of 2, okay? So 4, if we look at our table, is 2 squared. 16 is 2 to the 4th, and 64 is 2 to the 6th. We're also going to do the same for the next one. 8 times 16 is 128. If we rewrite that, 8 can be rewritten as 2 to the 3rd. 16 can be written as 2 to the 4th. And 128 can be written as 2 to the 7th. Now let's look at the last one. Again, 8 is 2 to the 3rd. 32 is 2 to the 5th. And 256 is 2 to the 8th. Now that all the bases are the same, they're all base 2, let's look at the powers. What kind of pattern do we see? Well, if we look at the powers in the first one, we have a 2, a 4, and a 6. So we can say 2 plus 4 equals 6. We know that pattern exists. Let's see if it holds true for the second one. We have 3 and 4, and together that does indeed make 7. So 3 plus 4 equals 7. And that works for the third one as well. 3 plus 5 equals 8. So we can multiply powers that have the same base by adding their exponents, and that is the product rule. For any number a and all integers m and n, you can multiply two things with the same base by adding their exponents. So a to the m times a to the n equals a to the m plus n. So when you're multiplying things with the same base, you're going to add their exponents. So let's do some examples with this. We have 2n times 3n. Well, the 2 times 3 gives us 6. And then n times n, that's n to the first, times n to the first. So that's going to be n to the 1 plus 1. And that gives us 6n squared. For b, we have 4 times 2, and we also have x squared times x to the third. 4 times 2 gives us 8. And if we use the power rule or the product rule on the powers, then we have x to the 2 plus 3, which gives us 8x to the fifth. For c, we have our 2's multiplied together, our x times x to the third, and our y to the third times y to the fourth. So 2 times 2 is 4. In the x and y terms, we're going to add those exponents since we're multiplying. And then we end up with 4x to the fourth, y to the seventh. For d, we have 2 times 2. We have a squared times a to the third, and b squared times b to the fourth. 2 times 2 is 4. Add the exponents in your a and b terms, and you end up with 4a to the sixth, b to the sixth. Now let's talk about the quotient rule. So we're going to again look for some patterns. So here we have powers of 3. I've given you a small table with some of the powers of 3 here. Okay? So let's start with the first one. We are going to write all of those numbers as 3 to some power. Okay? So the 81 is 3 to the fourth, 27 is 3 to the third, and 3 is 3 to the first. On the next one, we have 27 is 3 to the third, 3 is 3 to the first, and 9 is 3 squared. Finally, on the last one, we have 243, which is 3 to the fifth, 9, which is 3 squared, and 27, which is 3 to the third. So let's look at the pattern we have. Well, we've got a 4 and 3 on the powers on the left side of the first one, and then a 1 on the right side. So 4 minus 3 is 1. Let's see if that holds true for the next one. We have 3 and 1, and then equals 2. So 3 minus 1 equals 2. That works there. And then on the last one, 5 minus 2 equals 3. So here we've shown that you can divide powers that have the same base by subtracting exponents, which makes sense. If we're multiplying things with the same base, we're adding. If we're dividing things with the same base, we're subtracting. They kind of go hand in hand. And that's our quotient rule. For all integers m and n, any non-zero number a, you can do a to the m divided by a to the n is a to the m minus n. So let's do some examples of that. Example 7, we're going to simplify b to the fifth over b squared. Well, we're going to subtract those exponents, and that's going to give us b to the third. Another way to look at this example is to take b to the fifth and write it out as b times b times b times b times b, and b squared on the bottom is b times b. If you cancel two b's on the top and two b's on the bottom, you're left with b times b times b, which is indeed b to the third. Okay, so just another way of looking at it. All right, let's take a look at example 8. We're going to simplify a to the fourth, b to the third over ab squared. We're going to subtract, well, first of all, we're going to separate our a's and our b's into two separate pieces. We will subtract our exponents on our a term and our b term, and that gives us a to the third times b. Now let's move on to power of a power, or what you're going to refer to as the power rule. Let's take a look at a few things and see if we can find some patterns here. So we've got 5 squared to the 4th. We can rewrite that as 5 squared times 5 squared times 5 squared times 5 squared. If we use the product rule, we can add our exponents, and that gives us 5 to the 8th. So 5 squared to the 4th is 5 to the 8th. Let's look at another example. We have x to the 6th to the 2nd. Okay, we take a power to a power. Well, x to the 6th squared is just x to the 6th times x to the 6th. We use the product rule to add the exponents, and we end up with x to the 12th. Now let's see if we can find a pattern. We have 2 and 4 on the left side, and then 8 on the right. Well, we know 2 times 4 is 8. And if we go to the other one, 6 times 2 is 12. So we can find a power by multiplying the exponents. And that is your power of a power rule. For any number a in all integers m and n, a to the m to the n is a to the mn, or a to the m times n. So let's look at a few examples here. We're going to simplify each expression. So for a, we're going to multiply the exponents, and that gives us x to the 24th. For b, we're going to take x squared to the 4th by multiplying the exponents, and we're going to take 5 to the 4th, and that's going to give us x to the 8th when we multiply those exponents on the top, and 5 to the 4th is 625. For c, that 4th power is going to be applied to the 3 and to the x squared. Okay, so we've got 3 to the 4th times x to the 2 times 4. So that gives us 81 x to the 8th. Then for d, that 5th power gets applied to the a term, the b term, and the c term. So we're going to multiply that 5 by all of those exponents, and that gives us a to the 15th, b to the 30th, c to the 10th. Now let's talk about the zero exponent rule. There are 2 ways to simplify a to the 3rd over a to the 3rd where a is not 0. A cannot be 0 because we can't divide by 0. So here's the first way. We can take a to the 3rd and make it a times a times a on both the top and the bottom. And that, of course, is going to be 1. The other way to look at it is to use our quotient rule. A to the 3rd over a to the 3rd is a to the 3 minus 3, which is a to the 0. Well, if a to the 3rd over a to the 3rd equals 1, and a to the 3rd over a to the 3rd also equals a to the 0, then we can say that a to the 0 equals 1. And that's our zero exponent rule. For any non-zero number a to the 0 equals 1. So any number or any variable, as long as it's non-zero, taken to the 0 power is going to give you 1. So in example 10, if we take negative 3xyz and take all of that to the 0 power, you're going to get 1. That's it. It's as simple as that. In example 11, if we take all of that stuff that's in the parentheses and take it to the 0 power, you're going to have 1. It's that easy. So anytime you see anything to the 0 power, it is going to be 1. Now let's talk about negative exponents. There are 2 ways to simplify k squared over k to the 7th, where k is not 0, because again, we cannot divide by 0. So here's the first way. K squared over k to the 7th is going to be k times k over k multiplied by itself 7 times. If we cancel out 2 k's on the top and 2 k's on the bottom, we're left with 1 over 5 k's multiplied by themselves, which is 1 over k to the 5th. Well, we can also use the quotient rule again. K squared over k to the 7th is k to the 2 minus 7, which gives us k to the negative 5th. So again, like we did with the zero exponent, we can conclude that 1 over k to the 5th is equal to k to the minus 5. which means that anything to the negative power, you're going to move it to the denominator. And if it's already in the denominator, you're going to move it up to the numerator. So let's do some examples so you can see how this works. We're going to simplify 12x to the negative third. Well, we know because it is a negative exponent, we're going to take it down to the denominator. And that's it. That's all there is to it. For example, 13, we've got that x to the negative 2 in the bottom. Since it's already in the bottom, if we move it to the top, that's what we end up doing, 4x squared. So example 14, we're going to put together some of our rules and see what we can get. So we're going to simplify negative 6 r to the third, s to the fifth, over 18 r to the negative 7th, s to the fifth, t to the negative 2. So we're going to start by splitting up everything. We're going to put our numbers in one set of parentheses, our r's together, our s's together, and our t's together. Then we're going to use our quotient rule. In the case of negative 6 over 18, we're just reducing that to negative 1/3. We'll use the quotient rule to subtract, okay? R to the 3 minus negative 7 becomes r to the 3 plus 7, which gives us 10. S to the 5 minus 5 gives us s to the 0. And, of course, we brought the t to the negative 2 up to the numerator. Well, we know s to the 0 is 1, so that goes away. And we can pull our r to the 10th and t squared to the top, and we're left with negative r to the 10th t squared over 3. All right, this finishes up this section of exponents. We have one more section in this short unit, and that's coming up in the next video.